Okay, welcome back. This is the last section in chapter 10. It's on complex numbers. And it's just an additional kind of thing. So the idea was you started out with counting numbers, in grade school. Someone has called those the whole numbers or the natural numbers, the whole numbers, or the counting numbers plus zero. And they said those were all the numbers you need to know, right? So the naturals or the wholes or whatever you want to think of those. And then in like maybe the next grade level, we expanded that idea and said, hey, wait a second, there's also these negative numbers, right? So we call those the integers. And he said, wait a second, there's more to the world than that. We added in the rationals, so fractions and stuff like that. And I said, hey, there's more than that. There's these weird numbers like pi and radical 2. We call those the irrationals. And so now what we're going to say is, oh, there's even more than all of that. And we call those complex. Okay. So there's other kinds of numbers you can research online and probably look on YouTube, and they'll have some cool video for you. But yeah, you think of how I'd like you to think of complex numbers. It's just kind of another bigger dimension in your already existing concept of numbers. It's just expanding it out a little bit farther. Okay. Turns out we won't do too much with complex numbers, but they are there. And if you wanted to keep studying math, you could look into that. Okay. Okay. So how are we going to expand numbers in this way? We use this thing called the imaginary unit. So before we said you really can't take the square root or an even root of something that's negative, but we kind of lied to you, and it turns out you can. Okay? So back in grade school, they probably lied to you and say, well, you can't divide 9 by 4 because it doesn't work out. But really, you can. It's just, 2.5, right? It turns out later you could do that. So now it's the same game. We lied to you. We're going to allow square roots of negatives. And what it does is just, it'll grow your idea of the number system a little farther. So I is the imaginary unit. That's what we're calling a negative under a root. And if you square I, you'll just get back to your familiar integer, -1. Okay. So usually the way it works is I'll be marching my imaginary units out the back door and my perfect squares out the front. I think maybe the book will put them out in front, but I like to march them out the back. Okay, so here we have number 5, negative square root of 18. Okay, so we can factor this thing, right? We can say this is the same as the square root of. I'm going to factor out the perfect squares forward, and then the negatives out the back, the -1 out the back, right? Right, so you'll have a square root of 9, which will be 3, times the square root of 2 times the square root of -1. Okay, and then simplify. Square root of 9 is 3. So we have the square root of 2, and then the square root of -1 you can write as I. So 3 square root of 2i, or I think maybe the book kind of likes to write it 3i square root 2. So either way is fine with me. Okay. If you do put it out back, I want you to use hooks on your radicals so I know where your radicals end. Okay. See how I always say, okay, the end of the radical is there. Let's look at another. Here's number 8. Yeah, the square root of -28. So again, I like to march the perfect squares out the front. So 28 is the same as 4 times 7. And then the imaginary out the back. So I'll have square root of 4, which is 2, and then the square root of 7, and then the square root of negative 1, which I'm just replacing with an I. Okay, let's keep moving. Here's number 9. So negative square root of negative 108. So 108 is divisible by 36. So I have the square root of 36 times 3, and then we have the negative 1. So this is negative square root of 36 is just 6. Then we have a square root of 3. And then square root of negative 1 is just I. Our complex numbers, if you note my diagram here, any number we deal with is actually a complex number. So complex number, what the heck is that? It's a number that's one of these regular numbers plus an imaginary unit of some sort. So it'll always have the form a plus bi. But if you didn't have an imaginary part, so if the b was 0, you would just have a, which would put you back into the land of the irrationals and rationals, the real numbers. So in particular then, 14, we see our first example of a full-blown sort of complex number. These are all complex numbers, but any number you deal with is complex. But this one it really has that form, a plus, eventually this will be bi. Okay, so let's simplify it. 20 plus square root of 5, and then I march the negative out the back door. So this would be 20 plus square root of 5i, and that'd be it. Okay, so again, this complex number, in general, there's two parts to it. There's going to be a real part and then an imaginary part. So the complex numbers always have this form a plus bi. And when we write up our answers, we kind of want to put it in that form. Okay. So let's, and like I said before, a good example of that just came to my mind is for example, you can think of a fourth as a fraction, right? But, you probably wouldn't write it, you'd always write it like 2. Okay? So it's for complex numbers, you can always write 2 as a complex number. You can write 2 plus 0 i's. Okay, but in reality, you would never write this. You would just write 2. Okay. Anyways, let's take a look at adding and subtracting, and then eventually we want to be able to multiply these things. We'll begin with adding and subtracting. And basically, you're just adding the real parts together and add the imaginary parts together, and then you're done. So here's number 18. I have 6 plus 5i's, our first complex number, plus 4 plus 3i, our second complex number. So you'll add together the real parts. 6 plus 4 is 10. And then you add together the imaginary parts. 5i's plus 3i's give me 8i's, and that's it. To do subtraction of complex numbers, you'll have to, if it has the real and imaginary parts, you have to distribute. Okay, so 25 in particular, 3 plus 2i minus 5 minus 7i. So to pull this off, the first thing you have to do is to distribute the negative. So this will be 3 plus 2i minus 5 plus 7i. 3 minus 5 is minus 2. And then 2i's plus 7i's will give me 9i's. Okay, let's look at one that's a little nastier, and then we'll move on to multiplying. So 31, we have 2 plus radical 3i's plus 7 plus 4 radical 3i's. And again, the book may put the I in front of the radical 3, so hopefully that doesn't confuse you. But here we go. I have 2 plus 7 is 9. And then I have 1 radical 3i's plus 4 radical 3i's. That would give me 5 radical 3i's. Okay, let's move on to multiplication. And then, of course, we'll look at division. Okay, so just multiplication. I guess the rule of thumb here is whenever you end up with an I squared, which is basically just I times I, you're going to replace that with a -1. Okay. Okay, so let's take a look. Here's 33. We have 2i times 5 plus 3i. So you distribute. So the first one, it would be 2 times 5 is 10 times I. And then the second one, 2 times 3 is 6 times I, so I squared. And then you replace the I squared with a -1. So this would be 10i plus 6 times -1. So you'll have 10i minus 6. And in general, you want to put it into the real plus the imaginary part. So we're going to rewrite it as -6 plus 10i. So it's kind of like when you're writing your polynomial in standard form, you don't write 3x plus 2x squared plus 5. It's 2x squared plus 3x plus 5. Okay, so there's a standard order for writing this. And it's with the imaginary part second. Let's try 37. So I got -7i times 2 minus 5i's. I have to distribute. Okay, so -7 times 2 is -14i. And then -7 times -5 plus 35, and then I times I is I squared. Okay, so that'll be -14i plus 35, replace the I squared with -1. So I have, let's write that first, right? So -35 minus 14i, and that'll be it. Okay, so these examples, the first complex number, so there's 1, 2 complex numbers here. One complex number is 2i. The other complex number is 5 plus 3i. When I multiplied it together, this first complex number only had the imaginary part, so it just came down to doing a distribution. But if both complex numbers have real and imaginary parts to them, you have to end up doing FOIL. Okay, so problem 42, we have 8 minus 4i, that should be a 4, times 3 minus 2i's. So first outer, inner, last, and yeah, it's a FOIL. So let's go at it. 8 times 3 is 24. The outer minus 16i, the inner minus 12i's, then the last plus 8i squared. Okay, simplify. So 24. I have -16 plus -12i's. So that'll give me minus 28i's. And then plus 8 times I squared. I squared is -1. So replace it with -1. Okay. 24 plus -8 will give me 16. And that's my answer. Okay. When we do division, it's going to look a lot like rationalizing denominators. Okay. So we'll again encounter the idea of a conjugate. Okay. So basically, to get rid of the I term in the denominator eventually, we'll want to multiply in by its conjugate, which, if you remember, we just rewrite plus as minus, and it has a nice way of canceling stuff out. Okay. So in this case, I'll have 3 times 3 is 9, and then the outer minus 15i, and then the inner plus 15i, and then the last plus 5i minus 5i is minus 25. I times I is, again, I squared. Okay. And nicely, these two middle terms are opposites, so they cancel. I'll have 9 minus 25, I squared, I replace it with negative 1. So I just literally replaced it. And then a negative times negative, here will be positive, plus 25. And then you could add those together and you get 34. And at the end, you see, oh, hey, the imaginary parts went away. And that's what we'll want eventually. There's one small warning. When you're multiplying some of these things out, you'll want to rewrite it with your imaginary unit first. So always push out the I before multiplying. And we haven't seen this happen or be something to worry about yet, but it is in the exercises. So just in particular, number 55, I have negative radical negative 7 times radical negative 2. So the way they want you to do it is to first rewrite these as radical 7i times radical 2i. And then you'll have, well, radical 7 times radical 2 is radical 14. Nothing you do there. I times I is I squared. And then I'll have radical 14 times negative 1. I squared is negative 1. So negative 1 times radical 14 will just leave you with negative radical 14. So that's the answer. So what would happen if I didn't push out the I? Well, it turns out you'll get the wrong answer. So the wrong way is to use the product rule to multiply out this radical as radical negative 7 times negative 2. So it'll give you a radical negative times negative is positive 14. And you see the answer is different, right? So you want to always, if you have some sort of multiplication of a root with a negative in it, convert to i's first. Okay? Otherwise, you'll get the wrong answer. Okay, so that's just kind of a warning to the side. Let's go back to multiplication and division of imaginary or complex numbers, rather. So now we're looking at division. DIV, that says DIV. Okay. Okay, so we'll use conjugates to do this work. For example, 63, we have 2 all divided by 3 plus I. So to do the division, you use conjugates. And it's going to look a lot like what we did with rationalizing denominators. Conjugates. Okay, so in the top and bottom, you're going to multiply out by 3 minus I. You just take whatever's here and replace the plus with a minus. If you do it to the bottom, you have to do it to the top. Okay, so in the numerator, I have to distribute. So 2 times 3 is 6. and then 2 times negative I is negative 2I. Downstairs, first outer inner last, 3 times 3 is 9, first. Outer minus 3I, inner plus 3I, and then the last minus I squared. Okay, so I have 6 minus 2I. And the denominator I have, well, a nice thing happens, right? The 3 i's cancel, and I have 9 minus I squared, but we always replace I squared with negative 1. Then you have 6 minus 2I all over 9 minus negative 1 is the same as 9 plus 1. And that, of course, is 10. Okay. We want to simplify this thing. And in the end, we want to write it as A plus BI. And so I think the easiest way to do this is just to go ahead and butterfly it, as they sometimes call it. And so you'll have 6 over 10 minus 2 over 10 i's. And then simplify. So always make sure you simplify. 6 over 10 is the same as 3 over 5. 2 over 10 is the same as 1 over 5. And then I. Okay, so see, in the end, it has that form A plus BI. And that's what we're after. Let's look at maybe a couple more of these. So 69. We have 6I all over 3 minus 2I. Okay, so I need to multiply by the conjugate. So you'll have 3 plus 2I in top and bottom. And the numerator distributes, so you'll have 18I plus 12I squared. And the denominator, first outer inner last, so 3 times 3 is 9. The outer plus 6I, the inner minus 6I, and then minus 4I squared. The numerator, I'll have 18I plus 12 times I squared, which is negative 1. And the denominator, the 6 i's are additive opposites. And then you'll have 9 minus 4 I squared. And of course, I squared is negative 1. I'll simplify more. Rewriting the top, I'll have negative 12. You always want A plus BI form. So I put the real part first, plus 18I. Downstairs, it'll end up being 9 plus 4, which is 13. Then you could butterfly, and you'll have negative 12 thirteenths plus 18 thirteenths I. So we get 75. 5 minus 2I all over 3 plus 2I. So this time the conjugate is 3 minus 2I. So I'm foiling in the numerator. 5 times 3 is 15. First, outer, minus 10I. Inner, minus 6I. And then finally last, plus 4I squared. All over. 3 times 3 is 9. Then minus 6I, and then plus 6I. And then minus 4I squared. Combine like terms, so I have 15, negative 10 plus negative 6, negative 16 i's. and then plus 4, and replace the I squares with negative 1. Down below, the 6 i's will cancel, and you have 9 minus 4i squared is negative 1 again. Okay, in the numerator, I'll have 15 minus 4, which will give me 11. Downstairs, 9 plus 4 will give me 13. Then butterfly it. And we have 11/13 minus 16/13 I. Okay, one weird one. 79. I have 7/3i. Okay, and I need to do the division. So what the heck is the conjugate of 3i? Well, it turns out it's negative 3i. So remember, all complex numbers have the form a plus bi. Okay. So 3i, if you were to write it in its complex form, would have to be 0 plus 3i. So its conjugate must be 0 minus 3i. All you do is change the sign from here to here. So instead of 0 plus 3i, I have 0 minus 3i. And so I'm going to multiply top and bottom by minus 3i. Okay. So 7 times negative 3 is negative 21i downstairs. Negative 9i squared. So I get negative 21i all over negative 9 times negative 1. So negative 21i all over positive 9. That's the same as negative 21/9 I. You can always do that. And then that's the same as, well, divide top and bottom by 3. And you get negative 7/3 I. Look, one last topic in this section, looking at powers of I. Oops. Okay, and there's a pattern that happens here. Note what happens if I keep taking consecutive powers of I. So I is, of course, I, but if I square I, then I get negative 1. Right? So if I cube I, well, what is that? Well, hey, that's I squared times another I. And I squared, I said, was negative 1. So that would be negative 1 times I, which is negative I. Let's look at I to the 4th. So I to the 4th I can think of as I cubed times I. I cubed I just found was negative I. And then negative I squared. And you replace I squares with negative 1. So that equals 1. So what is I to the 5th? Well, it's I to the 4th times I, which will equal 1 times I, which will equal I. And what happens is you kind of have a repeating pattern. If you were to, let's not, go through all the details, but I to the 6th is just going to be negative 1. And then I to the 7th is just going to be negative I. And then I to the 8th is just going to be 1 again. Okay? So you see there's kind of a pattern that happens when you do this. It's kind of neat. So I, -1, negative I, 1. I, -1, negative I, 1. So I to the 9th is going to be I. Okay, so the book wants you to play around with this idea in order to simplify expressions. So let's look at some of those. Here's 85, and I have I to the 10th. So the trick, I think, is to rewrite it in terms of try to get an I squared. Okay, so I to the 10th is the same as I squared raised to the 5th. So remember, when you have powers to exponents, you're multiplying. So if I had a to the 4th raised to the 5th power, that would be equal to a to the 20th. So here I have I squared to the 5th. 5 times 2 is 10. Okay, so why would I want to do that? Well, you can replace I squared with -1. And then we know how -1 acts when we raise it to odd or even powers. If you raise it to an odd power, it'll just be -1. If you raise it to an even power, it'll be +1. Okay? So in this case, I get -1. Okay, so let's see if we can do that with bigger powers. The same idea. So here's 89. I want you to figure out I to the 22nd power. So I rewrite it as I squared raised to the 11th. 11 times 2 is 22. Then I squared is just -1. And negative to an odd power is negative. Let's look at 93. They want us to figure out I to the 17th. Okay, so the way I'm going to have to do this is kind of separate off one I. So I can rewrite this as I to the 16th times I. And then if it has an even power, you can do the trick that we were doing on these past two problems and rewrite that as I to the 8th, or sorry, I squared raised to the 8th, and then times I. I squared is -1, raise that to the 8th, times I. Negative raised to an even power will be positive, so that'll be +1 times I, so that'll just give me I. Okay, one more, and the clock quits. So this will be 97. And this time we have -I to the 9th. Okay, so one way you could think of it as -1 times I to the 9th. And then you have a product to a power. So this is the same as -1 to the 9th times I to the 9th. -1 to the 9th is just -1. So we can write -1. And then I to the 9th, I'm going to have to separate that into I to the 8th times I to the 1. Then I to the 8th, I'll have -1 times I squared to the 4th. Sorry, I'm totally just ran out of room. Let me try that again. So let's get it again. 97. I have -I to the 9th. All right. So what I said is you could think of this as -1 times I raised to the 9th. And then you have a product to a power. So you can raise each one of these guys, the -1 to the 9th, and then the I to the 9th. -1 to the 9th is just -1. So I have -1 times, and then I to the 9th. I want to rewrite that as an even power times I. So I to the 8th times I to the 1. I to the 8th I'm going to rewrite as I squared and then raised to the 4th. And then you have -1 times I squared, of course, is -1, raised to the 4th, and then times I. So you have -1 times negative to an even power will be +1 times I. -1 times +1 is -1 times I. And -1 times I is just -I. Okay, thanks for watching. Bye-bye.